First talk is by Stier from Oxford University. He's going to be talking about probabilistic AI for clouds and climate.
Thank you. So I'll try to give, I know it's a fairly broad audience, so first I'll try to convince you why you should care about clouds. And then we talk a little bit about climate and how this relates to AI. And I hope I can stir up some discussions that some of us might be able to follow up later on. So first thing we get as climate scientists, generally the question, isn't the science done? And the answer is generally it's done enough to act, so that's done, but there's a lot of uncertainties left. And when you think of it, we don't understand Earth's climate sensitivity fully. How warm will it get? And I'll come back to that. We don't fully understand, or we really don't understand well, the regional impacts of climate change. And then we also have to think quite a bit about the mitigation options, what we need to do. And the more you dig into it, the more you realize it's very often clouds that get in the way of this. So when you talk about clouds, you speak at Isaac Newton Institute, and people think clouds. That sounds like a trivial problem, but they can also think of it. You think about a turbulent flow, multiple phases, multiple morphologies, interaction with radiation. It's as complicated as it gets, unfortunately, and that gets generally in the way. So why do they matter for climate? Well, clouds have a net radiative effect of about minus 20 watts per square meter. Means probably nothing to most of you. Does anyone know the net radiative effect of anthropogenic CO2? Roughly? 2. Okay, so clouds have a 10 times bigger radiative effect than the anthropogenic effect of CO2. So if you change clouds by 10%, we could either double or offset the whole thing. So it does matter what clouds do in a changing climate. In addition, they obviously control the hydrological cycle. So a lot of the climate impacts are driven by clouds. So if we don't represent them well in climate models, we probably have a problem. So let's see how well we do. And this is a slightly complicated plot, so give me a little bit of time to introduce you to it. So this is an analysis of climate feedbacks in the last 2 generations of climate models. And each little circle is a climate model. In blue, you have sort of the previous generation. In orange, you have the sort of the latest generation. And this gives you cloud feedback parameters, which are basically how many additional watts per square meter you get per degree of warming from a feedback process. Okay? And there are some things that are quite well known, like Planck feedback, just the radiative response, or then the response to relative humidity. And you see basically, yes, there are feedbacks, we understand them, and models totally agree. There is not a lot of diversity between these processes. There's more diversity already when we come to albedo feedback, so changes in albedo, land surface albedo in a warmer climate. But then the big elephant in the room is clouds. So cloud feedbacks are vastly diversely represented in these models, and they drive a lot of the uncertainty in our climate predictions. So that's one reason why we should care about clouds. It's a bit hard to point here, but I'll try. And you also see then, when you translate this into this property equilibrium climate sensitivity, how warm will it get if we were to double CO2? Then you see that between the last generation of climate models in blue here, and the current generation, or the latest generation, the diversity has increased. So we're getting worse at predicting climate. And some of them actually have predicted a very, very high climate sensitivity here. And this actually happened to be driven by clouds. So you hear a pattern from what I say. So it's gone, the diversity from clouds is contributing a lot to this. And the uncertainty has gone up. And just for a side note, actually the Met Office model is one of the models that got really warm, so it's very much on the top of that chart. So why? Well, one thing, and that is slightly annoying for machine learning, a lot of this particularly the high climate sensitivity issues here, have been really driven by state-dependent cloud phase feedbacks. So that stuff, state-dependent, never sounds great if you want to generalize. And it's stuff that was related to the cloud phase. So I asked ChatGPT to help me illustrate this, and it did. So you can think of it, in a certain climate, we always have cloud droplets and ice crystals in the atmosphere. And if you go to a warmer climate, you have less ice crystals and more cloud droplets. And as it happens, if you have the same amount of water and spread it over many small droplets instead of big ice crystals, it's more reflecting. So climate models used to have a negative feedback loop that as you go to a warmer climate, you get more droplets, less crystals, and they cooled themselves down by that a little bit. In the latest exercise of this climate model revisions, some climate models, including the Met Office model, based on observations, improved the representation of liquid versus ice and actually made the clouds more liquid in the models, because we know from observations there's more supercooled water than people previously assumed. And effectively, we've taken away this cooling mechanism. And boom, these models got very warm. So that is just an illustration that sort of generalizations of, if we go from weather to climate, is quite a complex bit. And in particular, if you have state-dependent feedbacks, then you have often a problem because you wouldn't capture this in your training regime with present-day observations. So we've seen, so basically all of this serves to introduce that we probably should care about it, and we should try to get it well in our climate models. So actually, we've seen already twice or 3 times the same plot, so I'll basically skip over some of this. This is just basically how traditional weather and climate models work, and it's making the same point as Rich did before. We know the equations, so fundamental conservation laws. We solve them on a sphere in this case, and we have a sort of a grid typically over the sphere, and we solve the equation on this grid, so you can have a spherical harmonics or whatever you want to do to represent these. And so we know that quite well, and it's quite accurate. The problem is the grid spacing in typical climate models is still on the order of 100 kilometers. And that means things like clouds that do matter can't be resolved. And then we have all these parametrizations in here, and there's a long list of parametrizations. And a lot of the uncertainty in exactly these feedbacks I showed before and other bits come because of uncertainties in parametrizations. So there's a big push to overcome some of this by brute force. And this idea of these high resolution or kilometer scale weather and climate models, and we can run them now for decades. It's quite impressive. And the idea is basically if you go down to kilometer scale or sub-kilometer scale, Japanese can go to 100 meters or something, then you actually begin to really fully resolve this cloud dynamics, and you can switch off some of these parameterizations that we don't trust, which is great, but expensive. So we can run them on the biggest computers for decades now, but that's not long enough, typically for long-term climate simulations. So for quite some time, we probably have climate models in lower resolutions for long-term runs, and some high resolution for process studies. Just to illustrate this, this is just the world as it would be seen maybe by a sort of traditional current climate model, and you see then when you zoom in over an area here over Africa, for example, this just shows the cloud, water and ice, so just to illustrate the resolution here. And you see that, yeah, you don't resolve any of the structure, you just have these big blobs, and obviously if you live somewhere in Nigeria and want to assess changing flood risks in 100 years, you might struggle a little bit to believe that this captures everything in your catchment area of your rivers or so. And then when you go to these high resolution models, we begin to really capture quite a bit. This is, I think, only a 5-kilometer run, but you really get some more fidelity in these models that they have the potential to resolve all of this well. But how well they do is a little bit open, and we come back to that later. But so, as a whole, we need to represent clouds well. And because clouds are sort of in a turbulent flow, in a very, very dynamic system, it is typically some sort of it's a stochastic phenomenon, and that we have to represent as well. So let's start off with some topics around low-resolution climate models, and that's work a PhD student from Hannah Christensen, and working with Hannah Christensen and myself, Greta Miller, has done a really interesting work. And the idea here is really how we can improve sort of representation of convection in some of these low-resolution climate models. And specifically, we focus on just what's called the trigger function that's in any of these climate models that tells the model, hey, now you have to switch on your convection scheme because it doesn't run all the time. So you have to predict that. And the idea we've done here is basically we just took a sort of a observation of the southern Great Plains in the US, and we have very high accurate observations there. And we take a lot of sort of input variables that represent the atmospheric state, and we try to predict the probability of convection occurring in the circle here, which is where we have a good measurement array. And you can feed it a lot of these parameters, and you can actually train the model quite well. And what comes out of it is this is the probability of convection as a function of time of the day. And you see there's some of these traditional schemes that don't work particularly well, but the model, so in green is here, it's not particularly clear, but in green is the model we're working with. It does really well, and as well as of the two best other schemes that both work on the prediction of convection based on dilute CAPE. If you haven't know about dilute CAPE, it's just a measure of the atmospheric stability in total. I won't go into any more detail than that. But so this model does really well. It doesn't exceed necessarily the accuracy here of the d-CAPE convection trigger, but it does quite well. What is nice though, because we trained this model on the atmospheric state, we can now interrogate the model to understand a little bit what drives the occurrence of convection. And the way we do this here, we go in the sharp value space, so we basically look at the importance of inputs for the prediction of the outputs, and we have this sort of n-dimensional sharp value space, and we can cluster it. And just to illustrate here, this clustering just in sharp value space, these are sharp values for different of these atmospheric parameters. And when you do this by clustering in the sharp value space, you then can look at the probability of convection per your cluster. And it's quite nice when you then look at this. There's, for example, clusters 1, 2, 3. I think it's quite unlikely that there's convection, but you also see that the different atmospheric drivers might really tell you this. So you can not just, it's not a black box as so many people always say. You can actually learn something about the atmospheric physics by training these models and then interrogating them later. And you also see, for example, cluster 3 and 4 are both not exactly certain what they are, and we can also interrogate them a little bit. What are the atmospheric drivers for that? So that's for the southern Great Plains in Oklahoma, so it won't solve many of our problems. So Greta's done the next step. So instead of just predicting probability of convection at a local site, we now do this with satellite data as well. So here the idea is you take, again, the input and atmospheric state with various different input parameters. This comes here from ESMWF reanalysis. We train a slightly different architecture here. There's not a forest. It's basically a very, very small neural network. And we predict the probability of convection as observed by the GPM satellite. So it's very similar. And we just see how that works. And actually, when you look at it, it works actually remarkably well. So on top of it is basically the observation, the observed frequency, and at bottom you see the predicted probability. So that represents really the sort of the observed precipitation that is attributable to convection very well. So this is nice, and this is something that Greta has then also gone on to implement in a climate model and is testing this and see how it improves the climate model forecasts. So it's nice ongoing work. One thing in these low-resolution climate models, as you've seen in this movie I've showed before, they don't represent the structure of clouds. And clouds are stochastic. So it's a very abstract phenomenon. Now, as we go to high-resolution climate models, we suddenly represent the structure of clouds. And then we have to think really of new evaluation strategies, because in a traditional model, because you don't represent the structure, people have just simply aggregated observations over large domains and in space and time, because that's, you want to only get it right in a statistical sense. But now we have a much stronger constraint, because we have to get the structures right. So that's a project we've actually, another PhD student working with Hannah Christensen and myself, Lily Feisham. So we've worked on a probabilistic framework to assess how well does a kilometer scale climate model simulate cloud structures as compared to observation. And the idea here is it's a likelihood-based framework. We basically, first of all, we generate data sets that are comparable on the same grid between observations and models. So we use satellite observation from geostationary satellite. And then we have this in the same representation, also kilometer scale simulations. Then we train a likelihood-based model and normalizing flow models on the observations. And it gives us then the likelihood distribution. And then from this model, we can compute likelihoods of observations and the simulations. And we can compare them and see, and that gives us a good insight in how well the structures of clouds are represented in kilometer scale models. So you can plot then here sort of the likelihood distributions, and you can calculate some divergence metrics, and it gives you a quantitative metric. How far away are the structures of these two models from the observations? And then we can actually plot this distance function as a function of time or space to assess a little bit how the model is performing. For those of you who know a little bit about convection, timing is particularly important, so time of the day, because traditional weather and climate models really struggle to get the diurnal cycle right, because it's quite hard. So let's see what this looks like. So this is now an assessment of 2 kilometer scale models, so the IFS ESMWF model and ICAN, Max Planck model, and German Weather Service, and as compared to GOES, the satellite data. And you see that the likelihood distributions all look roughly broadly similar, but you see also that the IFS model here, even by IUC quite clearly, it's quite a bit further away from the distribution of the observations. So this is nice, and you can calculate the distance metrics for that, and we get a good insight in sort of model performance based on just the structure here of these fields. We can also plot this on a map. And on a map, it looks like this. So you see basically the log likelihood from GOES, the satellite, from IFS and from ICAN, and the difference, the distance, distance or difference is in this case the same, between the two. And you see really in IFS this big cloudy band, the ITCZ really seems structurally different than as in ICAN. And what this means in terms of the cloud physics, we don't know yet, but it's interesting to find out. So this is just a way to look into it. And it's a paper that's just submitted to ICLR. So, and moving on a little bit from there to the concept of more machine learning based models in general as a tool for climate prediction. We've seen from Rich and others that these weather models doing fantastically now. And they basically, physically, climate models are weather models that you just run a bit longer. And we see now that these weather models, the rollouts are stable for many of these models for a longer time. So will they then just replace climate models? So does it mean the same revolution that actually in weather forecasting took less than a decade? Will that happen in climate modeling? And there I'm quite skeptical. I'll just show you one thing, and it comes back to this generalization. So cloud feedbacks is, for example, one thing. It's a state-dependent feedback. You won't find it in your training data necessarily, so it's quite difficult. So how well do these models generalize? And this is actually a nice illustration here from one of our Intelligent Earth students, Maren Höfer, who basically worked with Milan Kluver to just do a very simple test for a hybrid weather and climate model, the neural GCM model, and just basically took the Earth and spin it the other way around, or to flip it upside down. This shouldn't be a problem for a physical model, because you just solve the physical laws. It shouldn't be a problem for neural GCM in principle. In principle. So that's what the Earth looks like then, if you do this. So this is just showing here the temperature, surface temperatures. And you see here it's just flipped upside and down, yeah? And you see in the upside down model, you see things like Africa. Yes, it has higher temperatures than the surrounding oceans. So yes, we have a land-sea contrast. That's plausible. But you also see that the model has some really funny ghost features. So there's ghost Rocky Mountains here, which are based, they would be in the middle of the ocean. And it has a ghost Himalayas and ghost Antarctica. So these things are not in this model at the moment. But as it happens, as they trained the encoders for neural GCM, they put some locations in. And thereby it doesn't generalize. It's a fixable problem, probably for them, but it's still sort of just a simple example that generalization doesn't necessarily come for free. So the last thing I briefly want to touch on is sort of where things may go and what we find interesting. And there's obviously many directions things can go. We've already heard nicely from Rich today about Aurora, and sort of the idea of touching on Aurora, the idea of sort of these big foundation models for the Earth systems, where you have basically multimodal data. And this is super fascinating and interesting, and I think it captures a lot of the things we can do already. But for me as a cloud physicist, there's not enough clouds in there for now. And there's definitely not enough cloud physics in there, I think, to capture some of these feedbacks. And that's something we as a group are interested to add to this. So I'll just give you some ideas what we're working on rather than giving you the final results, because we don't have them yet. But with Tim Reichelt, we have a project where we just now start with geospatial foundation models for clouds. And the idea is really we do conditional generative modeling, and we just want to go from atmospheric structures. There's on the left-hand side, terrible plot if you don't know it, taphigram, would take far too long to explain, but very insightful for the atmosphere. But this tells you all the state about the atmosphere, and then we encode this in some latent space and learn what controls the atmosphere in this latent space. And then we want to train generative models to initially just predict cloud fields and see how well we can represent them. But nothing will stop us at just 2D cloud images. They're not particularly useful, but I think they're sort of a necessary criterion to get these right. Perfect, yeah. I think we can go much further than just cloud fields, and I can give you some hint that this also may work by thinking about the cloud vertical structure. And this is results from a project from the ESA FTL, so the Frontier Development Lab collaboration. If you haven't heard of it, it's quite an interesting way, like intense sprints of small groups of researchers. And this team, I think 4 people from our department were involved. And they worked hard on basically the idea of 3D reconstruction from 2D satellite data. So here you take 2D satellite images from GOES, again, a geostationary satellite imager, and you train basically this model first, pre-train this on large geostationary satellite data sets. You see they started off with something like many terabytes here. And then you fine-tune this model to make prediction of what CloudSat would see. And CloudSat is a cloud radar. So it gives you a vertical profile of the atmosphere, the vertical structure we're really interested in. And you see a nice illustration of what this looks here. Then from this 2D images, it would basically make a prediction what the CloudSat slice would look like. It's even nicer shown in a movie. So this is now then applying this model to the Hurricane Dorian when it just before it did landfall in the US. And you see basically what goes into it is this geostationary satellite images, and it produces then really the model slice through the storm as seen from a cloud radar. And it also gives you the cloud radar reflectivity that you would observe. It's obviously a little bit hard to evaluate, so some of this is still ongoing. This isn't an entirely solved problem, but the early evaluations that this group and other groups in similar spaces have done are really promising. And you can recover quite a bit of 3D structure from 2D images. We can talk in more detail what the underlying physics might be, or where the information content comes from, but it's interesting. So it's a paper that's accepted for NeurIPS, the Climate Change Workshop. And the last thing I want to briefly touch on, and coming back a little bit to the idea of interpretability, because it's all nice if you train sort of foundation models. If you don't understand them, it's sort of not as meaningful. So there's some ideas, though, I think, how we can interrogate some of these models. And this is also work from an Intelligent Earth student, Alex Dover. It's also submitted to the NeurIPS workshop here. And the idea was to look into, this is again the sea bottle, the climate in a bottle that Scott talked about before, the climate in a bottle model from NVIDIA before. But the idea was, could you understand could you predict basically the gradients through this model to understand the sensitivity through this full model? And so what Alex has done very nicely in a very extended maps, which I won't explain and go into in the time we have, is to really calculate the sensitivities of this model. And just to give you one example here, so this would be now the sensitivity of this little patch shown in green with the troposphere radiation jet. How sensitive is it to the SST patterns, so the sea surface temperature patterns in the global oceans? And this is exactly one of these questions people are really interested in cloud feedbacks. There's this idea of the pattern effect, that different SST patterns project very different on the global radiation balance. But the nice thing is here is that you can really calculate these gradients through a model like this and work out sensitivities. So even if these models are very complicated, and this isn't entirely simple, there's some hope of interpretability. So this is just to illustrate that there is a paper. And I'll just end actually with one slide. I think everyone has their own favorite version of this slide, but in a way that's, I think, what the climate modeling landscape will at least look like for the next 10 years. Beyond that, I don't dare to make predictions. And I think there will be some high-resolution physical twins like Destination Earth and big high-resolution compute, and that will exist. There will still be a big generation of low-resolution climate models, and both of them will be somewhere between physics and hybrid AI physics. So I think this will definitely happen. But then on top is sort of badly illustrated, but the idea is there will be a new sort of generation of models which don't train on reanalysis and weather models, and the weather generator project is one of these. So at ESMWF is the idea that you purely train on data. But I think one thing that most people haven't worked yet into all of these concepts is how do we incorporate the really important information on these ultra high resolution models that you still need. To simulate cloud feedbacks, we need to go down to 100 meters or beyond. And all of this needs to come together in these models. So I think that's something for us to play with. But so that's the future for me. But clouds, we have to get right. And I'll stop here. I'll show some advertising.
Okay, we have time for a few questions. Yep.
You were showing kind of the overfitting to the spatial location where you have like a ghost layers or ghost Antarctica. Is that a big problem, given that the Earth is the right way up and it's the right way around?
I think it's a good example. Yes, no, we don't typically rotate the Earth the other way around. You're right. But if you change your sea ice and your clouds factor in that there's sea ice and there's no more sea ice because it's warm, then you're totally wrong. So I think it's just a nice illustration that these things get in the way. Yes, it's a toy example, but I think these are quite useful. And it's actually quite interesting because in this model, I think no one assumed there would be location, because there's absolutely no need to encode location. So we need hard test cases, I think. This was a simple one probably.
There was a question.
In your slide before this, do you have any ideas or directions of how those like high resolution LES DNS might be integrated to inform?
Ultimately, we can see them. I mean, I think it becomes a bit philosophical. So I think there's a group of people, and I like the ideas, want to just train on observations so that you avoid any model errors. The problem is when you do this, you're obviously limited by the observed state. And I think when we train these models, we have to probably monitor if we're still in distribution. And if the climate system pushes us, say, in a state that you've never seen, I think the only thing we can do is to switch on these models and train on these models as well, instead of the observations. That would be one way, but it's a bit clunky. I don't know yet how this may work, but it'd be fun to find out.
Okay, there's a question right at the back.
Yeah, thank you for the talk. Really great. I have a question about the likelihood-based approach you were showing with distributions of results. You were showing some multimodal distributions. Do you know why you were having that type of multimodality?
Was my first question too to Lily. To be worked on, yes. We're basically working on plotting this out. I mean, you can do this. We have to just plot it out, the physical parameters corresponding to each of these modes. We haven't done it yet, but exactly my first question too. There's no reason why it has to look like this, but it will tell us something. It is, though, very common, so we know, I don't know the specific answer about this, but in clouds, we observe generally multimodal distribution. So you often find in the tropics a trimodal distribution, deep convection, some congested, so still deeper convection, and then some low-level clouds. In a perfect world, it just corresponds to these modes. In reality, it's probably more complicated.
Thank you.
Yeah, Richard.
There was a really nice example from ECMWF of causality sort of being baked backwards in these models. So they had like rain spotting events, isolated rain spotting events, and they had a weather forecasting model. And it turned out the model would learn the inverse relationship between soil moisture and precipitation. So it had soil moisture causing precipitation rather than precipitation causing soil moisture. So sort of, do you think there might be a hope of fixing some of these issues through particularly well-chosen either training on counterfactuals or even the high resolution problem, targeted high resolution runs over a local area, which then we use the model to generalize. Do you see that as a conceivable way forward to sort of addressing some of these issues? Or do you think that's hopeless?
No, I'm totally optimistic. I mean, in 2018 we hosted in Oxford this workshop on AI for weather and climate modeling. And I went back to the conclusions of this workshop, and it's basically said not in the foreseeable future can we do medium range weather forecasting. And it's 8 years later we're there. I don't think this will happen in climate, but I think we'll solve it. But I don't see none of the climate models that are out and the climate emulators and Chris Bretherton or anyone, no one has a solution how to solve the cloud feedback problem. Because Chris Bretherton's team is doing they're learning the cloud feedbacks from a low resolution climate model, which they know that we don't trust. No criticism, but I think we have to figure it out, but it will take more time.
Okay, so we'll now move on to the next talk. So let's thank Philip.